Okay, we are going to begin. Bonjour. Donc, je vais faire la présentation en anglais pour Lisa. So, first of all, let me say that it's really a great pleasure to award to Lisa the second International Cours Peccot, which comes with a medal. So, congratulations and thank you so much for coming and giving this series of lectures. I'm just going to do a short introduction of Lisa, who has very impressive mathematical achievements. So she began by winning 4 gold medals at the Olympiad International of Math. She completed her PhD in 2019 in Stanford. Then I think went to MIT and Princeton Institute and is now a full professor at Bonn since 2023. She got already quite a lot of awards, among which the European Prize in Combinatorics in 2021. Lisa is really an absolutely outstanding expert. So first on the polynomial method in combinatorics, and she has found sophisticated extensions of the methods in order to obtain solutions of linear equations in dense sets for which all the variables are distinct, has many amazing results. She has also proved deep theorems that states that a quadratic form with 0, 1 coefficients takes the value 0 at large number of plus and minus 1 vectors, then it must have a low rank. She has determined the typical approximate size of permanent of a random matrix with plus minus 1 coefficients, answering a central and very difficult open problem in the theory of random matrices. In 2002, she solved a 50-year-old problem in voting theory by determining the asymptotic probability that there will be a Condorcet winner if 2k minus 1 voters each rank n choices. And just last year, she has obtained the first significant improvement since 1947 to the lower bound for the size of a subset of integers from 1 to n that contains no arithmetic progression of length 3. So we are very happy to have Lisa here. She will give this first conference today, and then on the 10th of February, the 3rd of March, and the 10th of March. Thank you very much, Lisa, for giving these lectures. Thanks.
Thank you very much. Thank you very much for this kind introduction, and thank you to all of you for being here and listening. As you probably read before coming here, the title of this lecture series is Three-Term Arithmetic Progressions, the Slice-Rank Polynomial Method, and the Erdös-Ginzburg-Ziv Problem. And today, I focus mostly on this first part about three-term arithmetic progressions, and we'll briefly mention the middle part, and you'll hear more about the middle part and the third part in the other 3 lectures. Okay, so we start with three-term progressions, or rather three-term progression-free sets. And so you can do this in several settings, and so we start with the most classical setting, the setting of the integers from 1 to n. So that's our first topic, three-term progressions, three-term progression-free sets in the integers from 1 to n. Okay, is it still working? Can you all hear me? Great. Okay, yeah. So, so we start with the following question, which is a fundamental and very classical problem in additive combinatorics. So here's the question. Given a large positive integer n, what is the maximum possible size of a subset of the numbers from 1 to n that does not contain a three-term arithmetic progression. Okay, so so maybe for completeness we should say what a three-term progression is. So you maybe know that already, but a three-term arithmetic progression consists of distinct x, y, z, so that x plus z equals 2y. So in other words, the numbers x, y, z are distinct, and the number y is exactly in the middle of x and z. Or another way you can think about this is to rewrite this as y minus x equals z minus y. So in other words, the step from x to y is equally big as the step from y to z. So that's a three-term progression. For example, the numbers 2, 5, and 8 form a three-term progression. And so now what we are asking is, we're given some number n, and look at this ground set of the numbers from 1 to n. So that's our sort of allowed universe, our allowed ground set now. And from there, we want to pick a subset. So we want to pick certain numbers of the numbers from 1 to n, but with the constraint that we do not contain a three-term arithmetic progression. And the question is simply, how many can we pick? So how big can we make such a subset? And in order to sort of talk about what's known about this question, let's introduce some notation for the answer. So let R3 of n be the answer. So in other words, R3 of n is the maximum possible size of a subset of the numbers from 1 to n without a three-term progression. So for example, just for concreteness, R3 of 7 is 4, because among the numbers from 1 to 7, we can, for example, pick the subset consisting of 1, 2, 4, and 5. That's a subset of the numbers from 1 to 7. 1, 2, 4, and 5. That's a subset of the numbers from 1 to 7. And within this subset, we do not have a three-term arithmetic progression. So you can check that you don't have three numbers where one is exactly in the middle of the other two. So that means this R3 of 7 is at least 4, because we can pick at least 4 numbers. And you can also check that you can't do better. So it's not possible that you, so let's say, for example, there's also other possibilities to pick 4 numbers, but it's not possible to pick 5 numbers. So it's not very hard to check that if you want to pick 5 numbers out of the numbers from 1 to 7, then you will have to have a three-term arithmetic progression. So that means that 4 is really the best possible here, and R3 of 7 is 4. But in fact, we do not care terribly much about what happens if we plug in certain small numbers like 7 here. The question is what happens for large n. So the question is, how does this R3 of n behave as a function of n? How does it grow with n? So that's really the question here. So maybe if we wonder sort of how does it grow as a function of n, let's start with some trivial observations. So clearly R3 of n is at least 1, right? You can pick at least one number. And it's at most n, right? Because that's the total size of the ground set. You definitely won't be able to pick more than n elements. But the question is sort of, well, how big is it actually? Is it closer to this? Is it closer to this? Sort of how does it behave? And a very important theorem about this was proved by Roth. Roth in 1953, who proved that R3 of n divided by n converges to 0 as n goes to infinity. So in other words, the ratio or the fraction of elements you can pick from this ground set is vanishingly small when n is large. So as n grows, the fraction of elements you can pick becomes smaller and smaller and goes to 0. And so it becomes sort of a vanishingly small fraction of the elements you can pick. Roth's theorem, that was not the original proof, but Roth's theorem can also be shown using the triangle removal in graph theory, which is a consequence of Simonetti's celebrated regularity lemma, So even though this is a statement purely sort of about numbers, it's a purely additive combinatoric statement, you can prove it with graph theory methods, which is in some sense surprising. Yeah, also let me maybe just briefly mention that an analogous result to Roth's theorem for longer arithmetic progressions was proved by Semeredi about 20 years later in 1975. So Semeredi proved in 1975 that if you fix any other progression length larger than 3, you have an analogous statement. So for any fixed k at least 3, if you define Rk of n, like here the 3 stands for 3-term progressions, but if you define Rk of n analogously as the largest size of a subset of the numbers from 1 to n without a k-term arithmetic progression, then Semeredi proved that also for any fixed k, at least 3 Rk of n divided by n also goes to 0. And so that is really a very deep result in additive number theory and was actually the main result mentioned in Semeredi's Abel Prize citation. Yeah, but this, today we'll be focused mostly on 3-term progressions, and so that was more like a side remark. So Roth in some sense answered that R3 of n, the question by saying that R3 of n is much smaller than n. So in other words, R3 of n is little o of n. That's another way to state this. But how big is it actually quantitatively? And so I guess Roth's theorem is now 70 years old, but over the last 70 years, people have worked very hard in trying to obtain better quantitative bounds. And so let me state, so this history of bounds, so upper bounds for R3 of n. And actually the problem of estimating R3 of n goes back almost 90 years ago to a paper of Erdös and Turan from 1936. So in 1936, Erdös and Turan showed that R3 of n is at most 3/8 plus little o of 1 times n. So they showed that the fraction of numbers you can pick is at most roughly 3/8. And then, as already mentioned here, this bound was improved by Roth. And so quantitatively, he showed that R3 of n is at most a constant times n divided by log n. And so that in particular then means that R3 of n divided by n goes to 0. And so then there has been a long sequence of other works. So let me maybe try to write them down in a more compact way. So each of those papers proved a bound of the form that R3 of n is at most n divided by some power of log n, where this exponent c here was different in each of those papers. So the first paper got a small positive c, and then the value was improved over, from paper to paper. So this is for certain constants c bigger than 0. And let me just mention that this one, the last one in this long sequence, so it went from a small positive constant just bigger than 0 to a quarter, and then a half, and 2/3, and 3/4, and 1. And then this paper obtained this constant strictly bigger than 1. And that was called breaking the logarithmic barrier. So getting beyond this sort of c equals 1 took, as you can see, sort of almost 10 years. And this sort of was called the logarithmic barrier and was really a big barrier for this problem. And so it was seen as sort of a huge progress that Blume and Zissas then managed to push this exponent to some constant strictly bigger than 1. And so just to compare to Roth's bound, so n is still the size of the ground set, and the question is sort of how much smaller than n do you need to be, what's sort of the correct sort of denominator here. And so here the denominator was just log n, and here the denominator is much bigger, so that's a much better bound because it's a power of log n rather than log n. Yeah, but then an even bigger breakthrough, to the shock of the whole community, happened around 2 years ago. So Kelly and Maker, who are actually computer scientists, they proved in almost exactly 2 years ago, I mean, the preprint appeared almost exactly 2 years ago, that R3 of n is at most n divided by 2 n divided by 2 to some power, and that power, 2 to some exponent, and that exponent is a power of log n. So it's n to the 2, n divided by 2 to the c times the 1/12th power of log n. So that bound is again much better than those bounds, because here the denominator is just the power of log n. But here the denominator is exponential in the power of log n. So that's way better. So this bound is way stronger than all of those previous bounds. And that's why this was such a gigantic breakthrough. Okay, I should also say for some constant. So this prefactor is positive. So for some positive prefactor here. And so then modifying this method of Kelly and Maker, so Bloom and Zisask, a few months later, sort of simplified the proof and slightly adapted the method, and then changed this 1/12th to a 9th. And that's still the best known bound. Okay, so the 12 is now replaced by a 9th, and that's where it stands. But so those two bounds are of the same quality, and they're much better than all of those two bounds, all of those bounds over there. Yeah, so these bounds on this list, certainly starting from here, were all proved with Fourier analysis methods. Yeah, so as I already mentioned, these new bounds here were very exciting. And that was not just because they were better than all of the previous bounds, but it was also because these bounds for the first time were of a similar shape as the already known lower bounds. So far we only talked about upper bounds, but let me maybe also, let me erase the board and write the lower bounds on the next board. So far we only talked about upper bounds, but of course if you want to estimate this quantity R3 of n, you also need to think about lower bounds and then ideally get those two bounds closer together. So let me now tell you what has been known about lower bounds. So a very old lower bound was found by Behrendt in 1946. And he showed that R3 of n is at least n divided by 2 to the 2 square root 2 plus little o of 1. So little o of 1 here stands for a term which goes to 0 as n goes to infinity. So some error term which sort of goes to 0 times log 2 of square root of log 2 of n. And so this lower bound is of a similar shape as the upper bounds over there, because it's again n in the numerator, right? That makes sense because that's the size of the ground set. And then the denominator is again a power of log n. Here it's the half power, right? Log n to the half is the square root n. So here it's the half power of log n, whereas over there it was a 12th or a 9th power. But at least the sort of quality of the term, or the rough shape of the term, is the same. And so that was also why it was so exciting when Kelly and Maker obtained this bound, because, when
you write log sub 2n, do you mean log n base 2 or what?
yeah, so log 2n, I mean binary log of n.
Yeah, that's the electron difference here. I think people in Paris always mean log when they write log sub 2.
Ah, okay, so how do they write binary log?
Log n over log 2.
Sorry, what? So I should just write log and then everyone will assume it's binary? Is that what you're saying?
Never mind.
No, I want to get it right. I'm in Paris, but I just didn't catch how do you write a binary log.
I just write log n over log 2. But
log n over log 2.
Log 2n is log n over log 2. Yes. Log sub 2n means log n.
No.
No?
No, normally it's log n over log 2. I think in Paris also.
Do you disagree or?
Okay,
So let's continue. But
so we understand what you're
Okay,
saying.
so yeah, I write a lower 2, and the log for me will be the base of the log. And yeah, so I think for today, probably most logs will be binary. Like in the bounds, I previously said it didn't really matter what base you put on the log, because there were always these constant prefactors, which mean that it's irrelevant what base you take, it just affects the prefactor. So yeah, so okay. But here, since this is an exact number in the prefactor, it does sort of matter to at least specify, but yeah. Okay, so that was Behrens bound, and yeah, so as mentioned, it has sort of a similar rough shape as this Kelly-Maker upper bound. And so then, of course, you can ask whether, again, there was a long sequence improving this bound, of works improving this bound, given that it's almost 80 years old, but actually not. So this bound has only been improved basically one time by Elkin, and then afterwards with a simpler proof by Green and Wolf. But so they also only improved this little O of 1 term. So same bound with improved little O of 1 term. And since I didn't write out the little O of 1 term, I guess if it's written like that, it's just literally the same. Okay, so that was sort of, until recently, all the progress that was made on the lower bound. I don't think, the reason is that nobody tried, but it seemed like sort of difficult, and I'll explain in a moment, well, in a slightly similar setting, but sort of related, why it seemed very difficult to get beyond this. Ben Green actually even called this bound of Behrens both fairly natural and fairly unimprovable. Okay, so recently, though, we did manage to improve the bound a little bit, and so that was joint work with Christian Elsholtz, Zach Hunter, Laura Proske, and myself. And so we improved the bound to R3 of n is at least n divided by 2 to the c plus little o of 1 times square root of log 2n, where our constant c, so basically the only difference is that constant that constant factor here in the exponent, which used to be 2 square root 2, and so our c is 2 square root of binary log of 24 over 7, and that's less than 2 square root 2. And in case you want to convince yourself that that's less than 2 square root 2, so 24 over 7 is less than 4, so the binary log of this is less than 2, and so that term is less than that term. But if you now quantitatively wonder how big the difference is, 2 square root 2 is roughly 2.828, and this is roughly 2.667. So quantitatively, the difference between those two constants is not very big, as you can see, between 2.6 something and 2.8 something. That's not a big difference. But the point is to show that this constant is not tight. So even though it hadn't moved in almost 80 years, this constant in this bound, our result establishes that actually it's not the right answer. Okay. So it's also very plausible that our proof method, and I'll say more about this later, today, in the later part of today's lecture, that it's also plausible that our proof method can be used to obtain better values for that constant, because the construction sort of, relies on some sort of ad hoc pieces which you put together. And if you prove those sort of ad hoc building blocks, you automatically already get better values of this constant. Okay, but yeah, so I'll discuss this more later today. Yeah, for now, let me maybe mention that these Fourier analysis arguments in the upper bound, so I mentioned that these upper bounds, at least starting from here, were all based on Fourier analysis. And these Fourier analysis arguments are technically much simpler in the so-called finite field setting. So far we've always talked about the so-called integer setting, so the numbers from 1 to n. But there's also sort of the sort of analogous sort of world, the analogous other world, which is the so-called finite field setting. And in that world, those Fourier analysis arguments all become much cleaner and much simpler. And that has been part of the motivation for studying this sort of other setting, this finite field setting. And so that's what I want to talk about next, unless there are any questions so far. Okay. Yeah?
Are the lower bound obtained constructively or not?
So this lower bound is basically completely explicit construction. Of course, it always depends a little bit on what you mean by explicit, like there's a pigeonhole step. So, but you could, I guess most meanings of explicit are something about the sort of running time, and so that would be completely explicit in terms of any such meaning of explicit. This is not completely explicit, and we'll see later why not. Other questions? Yeah?
Is there also any conjecture about the right order?
That's a great question. So I think before this work came out, I'm not sure. I think different people may have had different opinions, but I'm not sure whether everyone sort of maybe even agreed that that shape is even the right shape. So now with this upper bound, we do know that this is the right shape. But now, of course, there are two questions. The big question is sort of what's the right exponent of the log n. So now in the upper bound, we have a 9th, in the lower bound, a half. And then the next question is what's the right constant factor. And I haven't heard anyone make any strong conjectures sort of in either direction. So but I can tell you for sure that this is not the right answer, right? Because it relies on this ad hoc step. And so that's definitely not, there's no way this is the right number. I mean, the point of this was just to show that this is not the right number. Yeah, I don't think anyone has really any. I mean, some people have conjectured that this type of behavior is the right bound. But now that we know that that's certainly not the right constant, I mean, among the people who believe that the half power of log n is the right answer, I don't think anyone has expressed any beliefs as to what the right constant factor is. And I also don't think that necessarily everyone agrees that the square root needs to be the right power. Although to me personally, that would seem very natural. And other people have also conjectured that the square root is the right thing. Yeah, but yeah, so maybe in short, there's no clear conjecture everyone agrees on. Okay, yeah, so let's move to the finite field setting. So now we are in the setting of fp to the n. So the n-dimensional vector space over some finite field fp. And we think of the field as fixed and n as large. So we can think of P as a fixed prime and N as large. And so then again, we have to say what the three-term progression is. So it's the same thing. So a three-term arithmetic progression in FPN consists of distinct x, y, z in fp to the n with x plus z equals 2y. So the same equation, still y exactly in the middle of x and z, but now everything is in fp to the n. So again, x, y, z are distinct things, this time distinct vectors in fp to the n, satisfying this equation. Okay, so then again we can ask the same question. And as I said, we think of the prime p to be fixed. And let's take the prime to be at least 3, because for 2 the question isn't sort of interesting at all. And then we take n large with respect to p, and we ask what is the maximum possible size of a subset of fp to the n that again does not contain a three-term arithmetic progression. Okay, so it's a completely analogous question to before. Just now our ground set is fp to the n, so this vector space over this finite field. And so then again we try to pick as many vectors as we can in it, but under the constraint of avoiding having a three-term arithmetic progression. And so that's the finite field. As I said, that's the finite field analog of this question we discussed before, and it has also been studied intensively. And so maybe on the topic of finite field analogs, I should also mention that actually there's a long tradition of considering finite field analogs of problems that were originally over the integers or over the reals. And maybe the most famous example is the finite field Kakeya problem, which was resolved by Dwyer in 2009. But that's sort of yet another example where people sort of intensively study the finite field analog of some question. And so in order to talk about what's known about this, we again need a notation. So again, let R3, and this time we don't write R3 of n, but R3 of fp to the n to signify that that's now our ground set. So let this be the answer. So in other words, let this be the maximum possible size of a subset of fp to the n without a three-term arithmetic progression. Okay, so let me explain what's known about this. And maybe to first get a feeling about sort of, well, I mean, maybe not everyone thinks every day about vector spaces over finite fields. So let's first slowly get a feeling about sort of how this problem works in fp to the n. So let's start with lower bounds for R3 of fp to the n. So let me first start with a very simple lower bound obtained by a very easy construction. So it's not hard to see that R3 of fp to the n is certainly at least 2 to the n. So how can we see this? So we can consider the subset formed of by all vectors whose coordinates are 0 or 1. So all 0, 1 vectors. That's 2 to the n vectors. And it's not hard to check that within this subset you don't have a three-term arithmetic progression. Because if you look at this equation here, and then sort of in every coordinate, every variable is zeros or ones, then it's not hard to see that the only way to solve this equation in each coordinate is if x and y and z are all equal in each coordinate, but then they are in total all equal as vectors, and so they are not distinct. So that means that indeed that's a three-term progression-free set, so we get this simple lower bound. But now, sort of basically what we did is in every coordinate we did something which is individually three-term progression-free. So we can take this idea a little bit further and improve upon it, and in every coordinate take something slightly bigger, but just still three-term progression-free. And so that's sort of called a product construction by taking sort of a product of different sets in every coordinate. And so if we take that idea sort of further and sort of now put a bigger progression-free set in each coordinate, we can show that R3 of fp to the n is at least R3 of p plus 1 over 2 to the n. So what's R3 of p plus 1 over 2? That's this R3 of capital N we considered before, whereas capital N we plug in p plus 1 over 2. And so the reason for having this bound is just we can, maybe let me indicate this here briefly. So take a three-term progression-free subset of 0 to p minus 1 over 2. That's p plus 1 over 2 many numbers, and you can see that you can take a three-term progression-free set of this size in it. And so we do this in each coordinate. And then you get this lower bound in total. So that's quite a bit better than that. But you can do yet better, namely Behrens' construction for giving a lower bound for R3 of n. You can also adapt very naturally to this setting, and then you can get, and I'll show the details of how to do that exactly later, then you get that R3 of fp to the n is at least p plus 1 over 2 to the n, and so that you can get by an adaptation of Behrens' construction. Okay, and I'll show you the details in a few minutes. So that's yet quite a bit better than this. Sorry, I forgot the lower order term. So n minus little o of n. Okay, and yeah, so this was then actually improved by Elsholtz and Pach in 2020 by improving this little order, lower order little o of n term. Okay, so Elsholtz and Pach had sort of the same bound, but a better little o of n error term here. I should maybe also mention that these are sort of the bounds which sort of hold for all primes p. If you care about a specific prime p, especially a specific small prime p, then there may be better bounds. So in particular, for p equals 3 and p equals 5, they're better bounds obtained by specific constructions just for those primes. So for p equals 3, the best lower bound is 2.2202 to the n, obtained by Romera Paredes et al. About last year with artificial intelligence techniques, yeah?
So here the small o of n is uniform in p or dependent p?
So that's for fixed p and large n. So it goes to, so this term divided by n goes to 0 as n goes to infinity while p is fixed. So there is some implicit p dependence here. But sort of the whole question is meant as for fixed p and large n. Yeah. And yeah, so yeah, on the topic of small primes, also for p equals 5, the best known lower bound is 3.271 to the n, which was obtained by Elsholtz et al. In 2023. So you can, so in other words, for small primes, for specific small primes, there are better bounds than the ones listed here. But sort of, I guess, until recently, sort of this was the best known bound that was valid for all primes p. Okay, so that was about lower bounds for R3 of fp to the n. of course, we should now compare to upper bounds, where clearly R3 of fp to the n is at most p to the n, but sort of what better upper bounds do we know? So Meshulam used these Fourier analytic techniques, which were also used for upper bounds for R3 of n, to prove that R3 of fp to the n is at most a constant times p to the n divided by n. So remember again, p to the n is the size of the ground set here. So clearly this is at most p to the n, but the question is how much smaller than p to the n is it? And so Meshulam showed that sort of if p is fixed and n is large, it's sort of little o of p to the n. So the fraction of vectors we can pick in fp to the n without having a three-term arithmetic progression again goes to 0 as n goes to infinity. And so in the bound he got sort of how fast does it go to 0? Well, so the bound is so the size of the ground set divided by n. Okay, and so this was then improved in the special case of p equals 3. So just for p equals 3, Bateman and Katz improved this to (3 to the n). So again, the size of the ground set, because we are in f3 to the n, now divided by not by n, but n to the 1 plus c. So this exponent of n, that's 1 here, was improved to 1 plus c for some small positive c. So this may seem like a minuscule improvement, but in fact this was seen as sort of as huge progress, and the paper appeared in the Journal of the AMS, so that shows that really this was seen as a very big step. But then, and even, and so these papers both use sort of Fourier analysis techniques like in the integer case. But then an even bigger breakthrough appeared as a preprint in 2016 with completely different methods, so not with Fourier analysis techniques anymore. And so that was the following theorem by Ellenberg and Reisweit. So the preprint appeared in 2016, but the paper was published in 2017. And so they showed that for any prime p at least 3, we have that R3 of fp to the n is at most cp times p to the n for some constant cp strictly less than 1, only depending on p. Okay, so this bound is much, much, much better than those bounds because it's exponentially smaller than p to the n. It's p to the n divided by something growing exponential in n, not something growing polynomial in n like these numerators. Yeah?
Yeah, I think the paper followed very, very quickly. Like the preprint was a few days after a preprint showing these four,
for Z1 over 4 to the n. Yes, that was sort of one of the next things I was going to say. So I was just, yes, so I will say something about sort of who introduced that method in just a second. But yeah, so just to compare those bounds, so this bound is really much, much, much better than those bounds because this bound is exponentially smaller than p to the n. It's p to the n. If you write it in this way, it's p to the n divided by something where that numerator is exponentially growing in n and not polynomially. Okay. So maybe because this is so important, let me write it down. So R3 of fp to the n is exponentially smaller. Okay, and so now let me go back to that comment. So as I mentioned, this proof did not use, this proof of Ellenberg and Reiswald did not use Fourier analysis techniques, but a completely different method, namely a polynomial method. And this polynomial method was introduced just a few days before by Claude-Antoine and Peccot for an analogous problem in Z modulo 4 to the n. So Claude-Antoine and Peccot studied sort of basically this question, but not in fp to the n, but in Z modulo 4 to the n, and proved a sort of similarly exponentially good bound there, and in their proof introduced a new polynomial method. And so this new polynomial method was then a few days later used by Ellenberg and Reiswald to prove this revolutionary bound for R3 of fp to the n. And so then still things happened fast. So then still a few days or weeks after that, Tao reformulated this method and sort of reformulated the proof of Ellenberg and Reiswald and this polynomial method of Claude-Antoine and Peccot. And his reformulation actually also generalizes this method. And this sort of more general version is now called the slice rank polynomial method, which is the middle part of this title. And so we won't sort of talk in detail about what this method is today, but in the next lecture on Monday, so this coming Monday in 6 days, I'll sort of explain how the slice rank polynomial method works in detail. And in particular, I'll show this proof of Tao proving this Ellenberg-Reiswald bound for R3 of fp to the n with this slice rank polynomial method. So that's Tao's reformulation of this Ellenberg-Reiswald proof. Okay, but that will only be on Monday because, we won't have time for that today. Okay, so that's this result of Ellenberg and Reiswald. So now, of course, you might also wonder how big is this CP. So it's very important that it's strictly less than 1, right? Otherwise this bound would be pointless if CP wasn't strictly less than 1. Clearly, R3 of fp to the n is at most p to the n. The point is that this is strictly less than 1. But the question is, how big is it now actually? And so the CP that this proof of Ellenberg and Reiswald gives, so the proof gives, well, depending on your notion of explicit and explicit value for CP, which is given by this. Maybe that's not completely explicit, but it's sort of, well, it's a one variable optimization problem. And so it's certainly, in some sense, explicit. And so now, okay, so now if you look at this term, it looks a little bit complicated, and it will be, I think, difficult to get a feeling for how big CP is just by looking at this term. But if you analyze this, and luckily people have done this actually even before, to analyze terms of that form, then you find out that this CP lies between 0.84 and 0.92. And as p grows, it converges against 0.841 and so on. Okay, so maybe don't worry too much about what this term is. This is just sort of maybe stated there for completeness. But the point is that this CP is very roughly 0.9 or 0.85. So if p grows, then it becomes very close to 0.85. And for small p, it's maybe more like 0.9. So that's the CP. Okay, and one other remark is that actually this theorem of Ellenberg and Reisweit shows that this R3 of fp to the n actually behaves very differently from R3 of n. So this theorem shows that R3 of fp to the n and R3 of n behave very differently. And this came very unexpected to the community when the result of Ellenberg and Reisweit came out. So indeed, so let's just make clear what I mean by that. So this bound we can rewrite as R3 of fp to the n is at most the size of the ground set p to the n to some exponent, and that exponent is, and I think this is maybe the only case today where the log is not in base 2. So that exponent is 1 minus the p base log of 1 over cp. So I mean, if you sort of do the mental arithmetic, this is sort of exactly this bound just written in a strange and convoluted way. But the point here is that this exponent, because the cp is strictly less than 1, this exponent is some number strictly this exponent is some number strictly less than 1. So it's 1 minus something small positive subtracted here. While on the other hand, already by Behrens bound for R3 of n, R3 of n is n to the 1 minus little o of 1. So if you write R3 of n as n to something, then that exponent converges to 1 already by Behrens lower bound for R3 of n. And so that means those problems behave, in some sense, have very different answers. In one case, it's the ground set size to some exponent bounded away from 1, and here it's the ground set size to some exponent sort of approaching 1. And I think that came very unexpected to most people in the additive combinatorics community at that point, who would have expected that the answers sort of should behave the same way. Okay, so okay, any questions so far? Okay, so then let's compare this sort of upper bound. Well, keep in mind that Cp is, say, roughly 0.85, and this lower bound. So this lower bound we could also write as Cp to the n, where in this lower bound the C would be a half, right? Here you have P halves, basically. So now both the upper and the lower bound for R3 of fp to the n are roughly C times p to the n with c equals a half for the lower bound and c being roughly 0.85, like in the limit this number for the upper bound. So we know that R3 of fp to the n grows like something like this, but we don't know what the c is. In the lower bound, we know it's at least a half coming from this lower bound, and the upper bound here we know it's at most roughly 0.85, at least for large enough primes p. So of course that now raises the question, what's the right answer for the c? And so, well, so of course, after this result came out, some people tried to improve the bound here, but nobody succeeded. But also people tried to improve this bound and improve that a half here, especially after that Ellenberg-Reisweit result came out and sort of it became clear that that term is the right term. People tried to improve the half in the lower bound. But that is also difficult, and let me try to explain why. So let me try to explain why this a half is sort of a significant barrier in this lower bound here, why it's not there just for random reasons. Okay, so let me try to explain why this is a barrier. So, so we can show that R3 of fp to the n is at least p plus 1/2 to the n divided by p squared times n. And so that's then p plus 1/2 to the n minus little o of n. And so that also addresses your question. So this little o of n here eats that denominator. So that means there is a p dependence, but if you want an explicit term, here would be sort of an explicit way to write the bound. So this can be shown as follows by adapting Behrens' construction for the integers. And so I want to explain how to do that to show why the c equals 1/2 is a significant barrier there. Okay, and also because it's a nice construction. So, okay, so how can we show this? We can show this by starting with the following sort of integer grid cube. So we take 0, 1, 2, and so on to p minus 1 over 2. So these are now p plus 1 over 2 many numbers. So we can think of them as sort of an interval of integers, so an interval of grid points, so an interval of sort of integer points. And now we take the nth power of this. So this we can now imagine as some n-dimensional hypercube with some intersected with the integer grid. So this is now a sort of box. And in every box, we have sort of side length p minus 1/2, and there are these p plus 1/2 integer sort of grid points, so possible integer coordinates for every side. And so now we have this big cube of grid points, and it consists of that many grid points. Okay, so far so good. That's a hypercube intersected with an integer grid. And so now we take that set of that many grid points, and we intersect them with a sphere. Let's, for simplicity, take a sphere around the origin. Like that simplicity, that sort of restriction only affects this by sort of maybe some constant factors down here, which don't really matter. So we intersect this with a sphere around the origin. Around the origin. Okay, so let's look at all spheres around the origin containing at least one of those points. Well, by Pythagoras' theorem, if I have a sphere around the origin and it's supposed to contain one of those integer grid points, then its radius needs to be the square root of an integer. And simultaneously, the radius can't be too big, right? The radius, the square of the radius will be at most n times p squared, in fact, even less. So that means that there's at most n times p squared different spheres around the origin, which altogether cover all of those integer grid points. And so now by the pigeonhole principle, we just take such a sphere which has the most points on it. So we take such we intersect it with a sphere around the origin containing the most points in 0, 1, 2, and so on, p minus 1 over 2 to the n. Okay, so how many points will that sphere have? Well, there were that many different spheres and that many grid points to start with, so one of them needs to have at least that divided by that many points on it. So that means we now found a sphere which contains that many as the fraction points from this sort of integer grid cube. So now why does that help us? So now we have this intersection set. So we intersected this with that sphere. Now we have that many points on the sphere. And so now these points on the sphere, the sphere is convex. So these points on the sphere can't contain a 3-term arithmetic progression just because the sphere is convex. So on the sphere surface, we cannot have a 3-term arithmetic progression. So that means we get a 3-term progression-free subset of this of that size. So we get a 3-term progression-free subset of this 0, 1, 2, and so on to p minus 1 over 2 to the n of size at least p plus 1 over 2 to the n divided by n times p squared. So that was the size. So we have found a subset of this size which doesn't have any 3-term progressions in it, if we consider this as a subset of Rn, yeah?
Sorry, I missed why there is less than p squared n spheres.
Okay, so the spheres, let's look at the square of the radius of the sphere. So that's an integer, right, by Pythagoras theorem. So it's at least 0, so that's an option. 1 is an option, 2 is an option, 3 is an option, and so on. But we also have an upper bound for the radius, because the radius is the sum of n different, for the n different coordinates of the square of this. So in every coordinate we get a contribution of at most p minus 1/2 squared. So in fact the radius lies between 0 and n times p minus 1/2 squared. So there is, so the radius, so r squared will be in 0, 1, 2, and so on to n times p minus 1/2 squared. And so these are now, I was a bit lazy because we don't want those sort of ugly looking terms and we don't care about constant factors, but these are at most p squared times n numbers. So there's at most p squared times n different radii. And so that means there's at most that many spheres, and so at least one of them needs to contain by Piccinor principle that fraction of points. Yeah, thank you for that question. Any other questions? Okay, so we're not done yet. So maybe another natural question is, why did we put that half here? That's still coming. So far we found a 3-term progression subset of this size. But what we needed was a 3-term progression free subset in fp to the n. Now, of course, you can interpret this so that every point here you can naturally interpret as a point in fp to the n. But you have to be very careful, because in fp to the n, you care about solutions to, well, the equation isn't here anymore, but to the equation x plus z equals 2y in fp to the n. So you care about solutions modulo p. You need to avoid having any solutions to this equation modulo p, whereas here we just avoided solutions to the equation x plus z equals 2y without saying modulo p, right? We looked at this as a subset of Rn. So we can interpret each of those points in a point in fp to the n, but we have to be careful that now with the modulo p, we don't create additional 3-term progressions which weren't 3-term progressions before. But now if you think about it, actually it's no problem, because if you look at the equation x plus z equals 2y and look at every coordinate, because all our points here had all coordinates at most p minus 1 over 2, if you look at the equation x plus z and on the one side and 2y on the other side, both sides will be at most p minus 1, right? It will be at most p minus 1 over 2 plus p minus 1 over 2. So in every coordinate, on either side of the equation, the things will add up to at most p minus 1. And so that means we can't get any solutions modulo p, which aren't solutions if we don't say modulo p. So the modulo p for the equation x plus z equals 2y makes no difference, because we restricted all points to have coordinates at most p minus 1 over 2, and so therefore we can't sort of get wraparound solutions. We can't get any wraparound modulo p because we restricted the coordinates in size.
Oh, I see. So this is a sphere defined, not defined modulo fp, but defined over the integer.
Yeah, this is all. So far there's nothing modulo p, and just this last step is doing modulo p. Because otherwise you couldn't use convexity, right? If you defined the sphere just modulo p, saying it doesn't have 3-term progressions because it's convex doesn't really make sense.
But you still have in fp that a hypersurface and a line are going to a sphere and a line are going to intersect in at most 2 points. It's just that spheres will be a lot thicker, that's all. No, but that's actually a good thing.
Well, yeah, so you only do modulo p here.
Okay.
Let me ask a very simple question. So, I mean, a line is of degree, what is
Yeah.
V2, so they can intersect at most in 2 points in FP or anything else, and the sphere cannot contain a line.
So it's, I think it depends on sort of, so the problem is the sphere can contain the entire line
Oh, so the sphere could contain.
At least I don't see any reason why, right? This is a multivariable thing, right? You have n variables, so if you have one quadratic equation in n variables, I don't think there's any reason to, any reason that would be able to tell you that you can't contain a whole line. Right? I mean, it is true that if you take a line in fp to the n and intersect it with a solution set of a quadratic equation, you can't have sort of on the line sort of. I mean, the thing either has at most 2 solutions or vanishes on the whole line, but it will vanish. I mean, there will be lines where the whole thing vanishes. So that's sort of why you can't sort of allude to convexity in sort of the fp to the n setting. That's why it's very important that you define your sphere in the Rn setting. Yeah. So in Rn, it's similarly, I guess, just to sort of maybe put some more clarity to the discussion. In Rn, it's of course still true if you take an arbitrary quadratic equation, then in Rn, the solution set can contain a whole line. So the quadratic equation can vanish on the entire line. But geometrically, we know that for a sphere, that's not the case. So the sphere has this nice convexity property that if you intersect it with a line, there will be at most 2 points. And you can't have 1 point on the sphere being in the middle of the other 2. Yeah, so that's where it's very important to do that part of the argument in Rn, and then only at the end we step to fp to the n, and then we have to be careful not to create 3-term progressions modulo p, but that's okay because of every coordinate is at most p minus 1 over 2, and so there's no wraparound modulo p. That was the thing I just explained before we started talking about this again. Okay, so this leads a 3-term progression free subset of fp to the n, since there cannot be wraparound modulo p. So with wraparound modulo p, I mean that sort of, you basically, if you think of this sort of like you go around modulo p to create more sort of 3-term progressions, which weren't 3-term progressions in the original point in Rn, but this cannot happen in the equation x plus z equals 2y. So for this equation, this cannot happen because we bounded all coordinates of all points to be at most p minus 1 over 2. So if we evaluate both sides of the equation in every coordinate, we get at most p minus 1. And so it's the same thing to have a solution modulo p or a solution without saying modulo p. Okay, so that means we've then found a 3-term progression-free subset of fp to the n of that size. And so that's that argument. But it's really crucial in this argument that we avoided this wraparound. And to avoid this wraparound, we had to restrict the coordinates by p minus 1 over 2. And so this c equals a half is really a crucial barrier. You can think about what happens if you do something different from a sphere and so on. And so you can try that. But you won't get, even if you replace the sphere by something else, you won't get beyond the c equals a half. And so, yeah, so that's why c equals a half really is a crucial barrier here. Okay, maybe let me write that down. Such an approach avoid round cannot be used to get beyond c equals a half. Okay. And so the next result I want to mention is a result where we did manage to beat the c equals a half, but as this sort of explained, we had to use a different strategy for that. And so that's again joint work with Christian Elsholtz, Kanter, Laura Proske, and myself in the same paper as the one we mentioned before. So we showed that there is a constant c strictly bigger than a half, such that for every prime p and every sufficiently large positive integer n, we have that R3 of fp to the n is at least c times p to the n. So we get this sort of bound for this constant c is strictly bigger than a half. And then, of course, again, a very natural question is how big is our c? So our proof works for any c less than square root of 7 over 24. For example, c being 0.54. So again, 0.54 is not so much bigger than a half, so not so much bigger than 0.5. But the point is to show that a half is not the right answer here. And given sort of this barrier for this wraparound, I guess it would have been a natural, well, I mean, it would have been plausible before that that was the right answer, but now we know it's not. Okay, so yeah, so again, quantitatively, the difference is not so big, but the point is sort of getting beyond the c equals a half barrier. And also, again, the 7 over 20, square root 7 over 24 is definitely not the right answer. Again, that follows sort of from these ad hoc pieces in our construction, which I'll say more about in the rest of the lecture now. Yeah, so if one improves these sort of building blocks of the construction, one would also improve this number. Yeah, and so I think the very interesting open question is now, what is the right answer for c? Well, we now definitely know it's not a half. It's also not this, because that came from some ad hoc construction. It could be the number coming out of Behrens' upper bound, which is roughly 0.85. It could be, but it's unclear. Yeah. Okay, so yeah, so for the rest of the lecture today, I want to give you an overview of the proof of this lower bound as well as the lower bound for R3 of n. So I mean, for time reasons, I won't be able to cover all details, but I want to show you roughly how the proof works and what this new approach is that we used to get this R3 of n lower bound and this lower bound. But maybe before we dive into that, let's take a sort of 3-minute break. Okay. Okay, yeah, so let's start again. So, yeah, so as I mentioned, I want to give a proof overview of how our lower, of the proofs of our lower bounds for R3 of fp to the n and R3 of n. And in fact, we prove actually a more general lower bound for finite abelian groups G, from which we then deduce both this and also the lower bound for R3 of n. So we prove a more general lower bound for finite abelian groups G. And so we should first talk about what's a 3-term arithmetic progression in G. It's again the same thing. So a 3-term arithmetic progression in G consists of distinct x, y, z in G with x plus z equals, well, for groups I shouldn't write 2y, but y plus y. So if x plus z equals y plus y, then x and x, y, z are distinct, then they're 3-term arithmetic progression. So then again, we should define a notation for the question we care about. So for this R, this sort of maximum possible size of a 3-term progression-free subset. So for a finite abelian group G, let R3 of G be the maximum possible size of a subset of G without a 3-term arithmetic progression. Okay, so yeah, so if we plug in G equals Fp to the n, then we exactly get this R3 of Fp to the n. Okay, and so as sort of many of us know, or maybe all of us know, a finite abelian group can be written as a product of cyclic groups, and so we really only care about, or okay, when we think about this, we can just write G as a product of cyclic groups. And so in this setting, we phrased sort of our lower bound so G can be written as Cm1 times Cm2 and so on times Cmn. And so then we have a lower bound of the following form, namely let m to mn be positive integers. So these are the size of these cyclic groups and factors. And let m be a common upper bound of them. So let m be such that 2 is at most mi. So these factors, I mean, these cyclic factors, we can make at least size 2, otherwise as much point. And so now so these mi are all at least 2, and now we let m to be large enough to be bigger than all of these mi. So in other words, we can take m to be the max of these mi's. And so then this bound states that R3 of Cm1 times Cm2, so of this resulting finite abelian group that we get by taking these cyclic factors, that this R3, so the maximum possible size of a subset of this abelian group here without a 3-term progression is at least 7 over 24 to the n over 2 divided by 10 to the 6 times m squared times n cubed times m1 times and so on times mn. Okay, so what does this term mean? So that's the quantity we care about for this abelian group written here. This is the total size of the ground set, so the total size of the group. And so now what fraction of the group do we have? So that's sort of the crucial term. That's this, but really what you should mostly pay attention to is the numerator. And at least in many contexts, the denominator, certainly in the context of this theorem, this denominator sort of is a lower order term that doesn't really matter. So it's really the numerator that drives the bound, at least for that theorem. Okay, so and yeah, so again we have the 7 over 24 showing up that we have there, and also this we had it sort of in the inverse form of 24 over 7 showing up in our lower bound for R3 of n. Okay, so that's sort of the more general version of the boundary proof. And so this now easily implies that bound as follows. Namely, we can take these mi's to be all equal to p. So this implies our lower bound for R3 of fp to the n by taking m1 equals and so on equals mn equals p. So if we plug for each of these mi's, we plug in p and we also take m to be p, then we get that R3 of Zp times Zp and so on times Zp, so that's nothing else than R3 of Fp to the n is at least 7 over 24 to the n over 2 divided by 10 to the 6. Then m we also take to be p, so then we get 10 to the 6, p squares n cubed times p to the n. And so now that's at least 0.54 p to the n, using the fact that the square root of 7 over 24, so 7 over 24 to the half is bigger than 0.54, and using the fact that n is large with respect to p, that these lower order terms sort of disappear in the inequality between, so we have this inequality that 7 over 24 is strictly bigger than 0.54, and that slack then eats up the lower order terms if n is large enough. So that means so what we've written there is implied by this here. And then, sort of with a slightly more complicated argument, this theorem can also be used to deduce our lower bound for R3 of n. So our 1 can also deduce our lower bound for R3 of n. Okay, and maybe for time reasons, I won't go into detail sort of how one deduces this. If I have time left at the end, I can sort of show the deduction. Maybe just to give a brief indication for now. So, so the trick to deduce a lower bound for R3 of n from this is to take these m1, m2, and so on to mn to all be co-prime, and so that their product is smaller than n, but smaller than capital N, but roughly capital N. Because then you have the inequality that R3 of n is at least R3 of m1 times and so on times mn if you pick them so that this product is at most n, and and that is at least R3 of z m1 times and so on times mn, because here you forbid more three-term progressions than here, because here you also exclude three-term progressions modulo m1 times and so on times mn. So you have strictly more restraints here than here. So therefore you have this inequality. And now if you pick m1 to mn co-prime, then you can rewrite this as m1 times and so on times zmn. And so now you apply this lower bound. And so that means in order to get a good term, you have to be careful about picking those things to be co-prime and each roughly like 1 over n to the roughly of the same size, but the product should be at most n. So they should each roughly be n to the 1 over little n. And so then, of course, maybe you have to be a little bit careful with how close you can approximate that if you want them to be co-prime. And then you need to optimize for this little n, and there's a little bit of a calculation. But that's sort of the trick. So you sort of use those ideas, and then you sort of optimize, and you can pick them to be prime powers, and use the prime number theorem to sort of say there's enough space to approximate. So there's a little bit of a calculation, and for time reasons, maybe I won't do it now. I can still do it if there's time left at the end. But it's not hard, so that's sort of, this explanation contained all ideas, the rest is mostly calculation. Yeah?
Which lower bound do you get for R3n?
That was the lower bound stated in the beginning of the earlier in the lecture. So I say just calculation, then you get our lower bound, which was this 2 times log 2 of 24 over 7 square root plus little o of 1 times square root log 2 of n. And then that whole thing times n. So it was that bound, and so that came out of that calculation. And maybe it's now believable that that number showed up because of that number showing up there. Okay, so yeah, so if there's time left, I'm happy to show the calculation. But maybe let's, for now, focus on what I think is maybe more interesting, namely how do we prove this. Okay, so yeah, are there any questions about the statement of this? Okay, so let's give an overview of how to prove this. Okay, so the first step is that we want to restrict ourselves to the case that n is even. We see in a moment why, but basically there's a simple trick which allows us to restrict to this case. So I claim that it suffices to show. And so I now mean it suffices to show in order to show that theorem. It suffices to show that for even n we have the following, which looks like this, but with a slightly better constant factor. So that we have, in the case that n is even, the bound for this R3 of this abelian group of 10 to the 5 m squared times n cubed times the size of the group. So this is the same term as there, just a slightly better constant factor. And so I claim that it suffices to show that slightly better bound for even n. Well, why is that? If we know this for even n, then it clearly implies this for even n, right? Because that bound is strictly weaker. So now we need to show that knowing this inequality star for even n also proves the theorem for odd n. So indeed, when n is odd, and we want to show the inequality in the theorem for odd n, then we can use a coset covering argument to observe that R3 of Zm1 times and so on times Zmn. This is at least, so that's what we care about. It has an odd number of factors, so we can't apply star, but we can say it's at least R3 of the same thing, but now with one additional factor Zm. So we had this common upper bound Zm. We now just write one more factor Zm, so we have an even number of factors. We have a bigger group now with adding one factor, but now we have to divide by m. So why is that? So this inequality is true for the following reason. If we have a three-term progression-free subset of this larger group, then I claim we find the three-term progression-free subset of this, of that size, of that fraction. The reason is just this group splits into m different cosets of this group. And so in one coset, we have at least that fraction number of elements in our three-term progression-free set. And so then that's a three-term progression-free set in here, because that coset additively is isomorphic to this. And so, so that means by that coset observation, we have that inequality. And so now this is an even number of factors. So assuming we already know star, we can now apply star. And so that means by applying star and calculating a little bit, you'll see that you get this back. So then we can, and then apply star to the numerator. So that means this coset covering argument allowed us to reduce to the case that n is even. So it allowed us to reduced to this slightly better bound with this better constant factor, but just in the case that n is even. So that means from now on we can assume n is even, and our goal is to prove this inequality star. Okay, so in order to, so that means we can now erase this theorem because our goal is now to prove this inequality for even n. And so the main step in the proof is to prove the following proposition, which I write now. And so that proposition really is the key difficulty. So for m at least 1 and even n, there is a measurable subset S of 0, 1 to the n with measure being at least that fraction here. Sorry, this is a typo. And the following property, such that for any x, y, z in S with x plus z, so we can think of this as a subset of 0, 1, the half open interval 0, 1 to the n, but we can think of this as a torus. We can think of S as a subset of the n-dimensional torus. And we're talking about a condition that says that for any x, y, z in S with x plus z concurrent 2y modulo 1, so in other words, we are talking about three-term progressions in the torus sense. So for any three-term progression in the torus sense, we have that x minus z infinity norm is strictly less than 1 over m. Okay, so what does that mean? The proposition says that for m and n, where n is even, there exists a measurable subset of the n-dimensional torus whose measure is reasonably large, namely at least this, with the following property. So the property is not there are no three-term progressions in the set S. In fact, it's a measure theory exercise that if you have a subset of the torus with positive measure, you will always have three-term progressions. So the condition is not to forbid any three-term progressions in S, but the condition is if we have a three-term progression in S in the torus sense, so that x plus z concurrent 2y modulo 1, then x and z need to be close together. So for any three-term progression in S, the outer points x and z must be close to each other. And what does close to each other mean? Well, the exact meaning is that in infinity norm, it's distant less than 1 over m. So that's the statement of the proposition. It's, we can find a large subset of the torus with large measure, so that in all three-term progressions in the torus sense, the first and the third point are close together. Okay, so far, this seems to have nothing to do with abelian groups and this. So let me first show you how this proposition, which talks about subsets of the torus, implies this inequality star. So maybe let me write that here. So we prove the implication that the proposition implies star. Okay, so if we assume the proposition and we want to show star holds, so that means we can take S as in the proposition. So let S be a subset of the torus as in the proposition. Okay, and so now from the set S, we want to construct a 3-term progression-free set of this. And so the way we do this is we embed this abelian group into the torus and then take the pre-image of S. And so our embedding will be randomized. So basically, we'll take maybe the most canonical embedding of this abelian group there into the torus, but then we'll take a random shift. So we'll take a uniformly random A in the torus. And we consider, so that's our shift, and we consider the embedding which maps the abelian group we care about into the torus, in some sense affinely, by sending any point R1 to Rn. So now R1 to Rn, R1 is a remainder modulo M1 and so on, and Rn is a remainder modulo Mn, and we send that n tuples of remainders to the point R1 divided by M1 plus A1 modulo 1, so and so on, to Rn divided by Mn plus An modulo 1. Okay, so by modulo 1, I just mean, well, go modulo 1 so that you lie in 0, 1. Or in other words, if you think of this in the torus as a natural sense, then you sort of take this point and then you sort of shift by A1. So maybe just to get some intuition for what that maps means. If you didn't have these shifts AI, so if you sort of omitted those AIs, this would be a very natural way to embed, so a very natural homomorphism from that group into the torus would be to send 0 to 0 and then sort of send R1 and so on to Rn, to R1 divided by M1 and so on to Rn divided by Mn. That's maybe if sort of we each sort of secretly had to write what we think is the most natural map from here into the torus, we would probably mostly all write that. Would be my guess. I mean, to me at least, that seems like the most natural way to embed this, to map this in the torus would be sort of this map without these A's. And so now we take this very natural map, and now sort of we shift, so we add sort of basically a constant term, this A. So we sort of shift with this A. So far that's a map, and it's well defined. So now what do we do with this map? Well, we look at the pre-image of S, right? S was a subset of the torus, so now we can look at its pre-image. So the pre-image of S is, I claim, a 3-term progression-free subset of Cm1 times and so on times Cmn. So I claim that for any A that we picked, and we picked this randomly, but for any A that we pick, the pre-image of S under this map will be a progression-free subset of this. So what's the reason? Well, if in this pre-image of S we had a 3-term progression, that means the 3 points of this 3-term progression would also be mapped to a 3-term progression here. So it's not hard to check that this map has a property that if you start with a 3-term progression here, it's mapped to a 3-term progression here. But so that means if this pre-image of S had a 3-term progression, then so that would correspond to a 3-term progression in S, so consisting of 3 image points of this map. But by the proposition, S has the property that any 3-term progression has the first and the third point close together. On the other hand, all image points on this map are spaced out. So all image points of this map, because we have this sort of grid-like way to map this here and then we just shift it, are far away from each other, meaning that the infinity norm is at least 1 over m, right? So the infinity norm so if you pick any 2 distinct points here, then you can look at any coordinate where they differ, and so then the corresponding coordinates here will differ here by at least n over mi, which is at least 1 over mi, which is at least 1 over m. Okay, so that means we don't have any 2 image points which are that close together. So that means in S there cannot be any 3-term progression consisting of image points. And so that means this pre-image is 3-term progression free. Okay, so that means this pre-image is a 3-term progression free subset. So now the question is how big it is. So how big it is depends, of course, on this A, but the A was random, so we can figure out how big it is in expectations. So it has expected size mu of S times M1 times and so on times Mn. Why is that? For every point here, the image here is uniformly random with a uniformly random choice of A. Because this shift here shifts, so that for any given point that I look here, this shift here shifts the image point around over the torus uniformly. And so that means every image point so for every point individually, the probability to lie in S is exactly this measure of S, mu of S, because for any point individually, the image point will then be uniform here. So every point has a probability mu of S to lie in the pre-image, and so since there are in total that many points here, the expected number of points in the pre-image is this. And so this is luckily now by this lower bound at least this. So in other words, we can pick an outcome of A where this pre-image has at least that size, then we found a 3-term progression free set of this size. So we found out that there exists a 3-term progression free subset of this, of at least this size, M1 times and so on times Mn. And if we now plug in this lower bound, we exactly get star. So that proves star. Okay. So that means we've now reduced our task to proving this proposition. Okay, and so in order to prove this proposition, basically we need to sort of, I guess, find this measurable subset of the n-dimensional torus. And we construct this subset from certain explicit 2-dimensional building blocks. And so these building blocks are described in the following lemma. So the lemma says, there is a measurable subset. So here the set we were looking for was n-dimensional, but the building block that is described in this lemma, measurable, that a building block is just 2-dimensional, so T is a subset of 0, 1 squared, with still reasonably large measure. So the measure of T is at least 7 over 24 minus 1 over n. And the measurable function f from T to the closed interval from 0 to 100n squared, such that for any x, y, z in T with x plus z congruent to 2y modulo 1, we have that f of x plus f of z is at least 2f of y plus x1 minus z1 squared plus x2 minus z2 squared. Okay, so the difference here is that here we are looking just for a 2-dimensional set, but then in addition we are looking for a measurable function, and this function should have the property that if in x, y, z we have a 3-term progression in the torus sense, then we have this inequality. And this inequality is a bit like Jensen's inequality. I guess Jensen's inequality for convex function tells you at a 3-term progression, the sum of the values of the function at the first and the third term of the progression is at least twice at the middle point. But here we get an additional slack term. So it's sort of like Jensen's inequality, but with some additional term here making it even stronger. And that additional term has to do with the distance between x and z. Okay, so the next thing to explain is how this lemma implies this proposition. So assume we have this two-dimensional building block set T. How do we construct our n-dimensional set S? So we prove the implication that the lemma implies the proposition. Okay, so if we assume the lemma, we can take T be as in the lemma. And our goal is to construct the S as in here, this n-dimensional set S. And so we define now S to be a certain subset of the n over 2-fold product of T. So remember, T is in 0, 1 squared. We want n, so that means if we take the n over 2-fold product of T, we are exactly in 0, 1 to the n, which is where we wanted S to be. So that's good. And that's also the reason why we wanted n to be even. Like that's is crucially used here. So now how do we define? So S is not equal to this n over 2-fold product of T, but it's a subset, and that subset is consisting of, so we define this to consist of those n over 2 tuples. So every element in S is an n over 2 tuples of points in T. So we look at those n over 2 tuples of points in T, which have the property that if we evaluate f at all of those n over 2 points in T and sum the values up, so if we look at that sum, we want this to be in some interval I, where I is an interval of length 1 over 2m squared. Okay, so why can we do this? Why can we find a set S? Well, we can define S in this way, but why can we take a set S in this way so that the measure is still that big? So in order to check that, let's just think about first, what's the measure of T to the n over 2? Well, T had measure roughly 7 over 24. So if we take it to the n over 2, we get roughly this. And we have to be a bit careful. We have a minus n here. But if we take to the n over 2 power, that only affects by a constant factor, and that goes into the 10 over 5. So basically, if we take just T to the n over 2, the measure will be this numerator divided by something like 10. So now we have this additional constraint. Okay, but so in order to satisfy this, let's just look at what this value, so this sum of these f values is for each point in T to the n over 2. So now, since each of these individual f values lies from 0 to 100 n squares, in total, this sum will be from 0 to 50 n cubed. And so we can divide the interval from 0 to 50 n cubed into subintervals of this length, and then we need on the order of m squared n cubed such intervals with some constant factor. That's where this 10 to the 5 came from. So basically, we divide this total interval from 0 to 50 n cubed into, well, something like 100 m squared n cubed subintervals of this length. And so then one of these subintervals will have at least the measure we want, right? Because this total measure of 7 over 24 to the n halves divided by, say, 10 divides into these 100 m squared n cubed subintervals. And so one of them will have at least that measure on it. And that we define to be S. So that's our definition of S. So if that was a bit fast, maybe just believe me that by analyzing and pigeonholing, you can find S of that measure with the property that if we define S this way to consist of those n over 2 tuples of points in T with this property for a well-chosen interval, we get a large measure for S. Okay, so now why is that good? So now we have S to be a large measure, but we still have to check that S satisfies this condition. So now, for any x, y, z in S with x plus z concurrent to 2y modulo 1. We want to check that x and z are close together, but we can check that as follows. So if we have such x, y, z with this, then in particular, if we look at every individual factor of t, then the corresponding components of x, y, z will form a three-term progression there too. So that means in every sort of each of those n over 2 components, we get this inequality. So that means if we add them all up, we have that f of x1, x2 plus and so on, plus f of xn minus 1, xn, plus f of z1, z2, plus and so on, plus f of zn minus 1, zn is at least 2 times f of y1, y2, plus and so on, plus f of yn minus 1, yn, plus all those error terms. So the sum of those error terms is the sum from I from 1 to n of xi minus zi squared. So that came just from taking this inequality in every factor of t and adding them all up. But so now this is an I, this is an I, and this is an and I is a pretty short interval. So because this all fits in I, but I is a short interval, that means that sum also can't be very different, very big. So that's sort of, now the length of I gives us an upper bound for the sum. So this now means that this sum, I from 1 to n of xi minus zi squared, is at most twice the interval length, so it's at most 1 over m squared, and so that means that the infinity norm of x minus z is at most 1 over m. So why was this implication? Well, we could write I as an interval AB with an upper bound and lower bound, and then you plug this in everywhere and calculate for sort of one line when you find this. So basically, if they're all sandwiched in this small interval, then that sort of slack between them must be small. That's sort of the idea. Okay, so for time reasons, I can't sort of do out the calculation. But that's a simple calculation, and then you get that. So indeed, S then has the properties as in the proposition. So then the last question is, how do we find the set T as in the lemma? So now we sort of are left with proving the lemma. And now I hope that the beamer still works. So that's the set T. So for time reasons, I won't attempt to draw it on the board. And the function I just write here, the function fab is the following. So fab is 24n squared times a plus b squared plus 6a squared if a is in 0.5, and 24n squared times a plus b squared plus 6a minus 1/2 squared if a is in 1/2, 1. Okay, so I mean this in this picture, by the way, where it says epsilon, you should think of 1 over n, because so that picture is from the paper and the notation is slightly different there. And I meant to write down an explicit definition of T at the board with some inequalities, and for time reasons I'll omit this, but I think the definition of T is also not very illuminating. So as this picture suggests, T is cut out by certain inequalities. So T is a union of certain polygons, and then the function f is some explicit function which is written here. And so both f and t are relatively simple in their definition. What they are exactly is also not terribly relevant right now. I just wanted to show you that they're really simple explicit things. And so then you need to check that for any x, y, z, you do have this inequality. And so that sort of takes maybe 2 or 3 pages of sort of analysis of T and how the 3-term progressions can be, and then sort of some simple inequalities. So there's sort of, once you found that set T and that function, it's not a deep argument to show that they have this property. It's sort of casework and sort of some simple inequalities. maybe what's surprising is that this whole approach works at all, so that you can find such a set T which is actually bigger than size a quarter, having this property and the function, so that this whole argument works. But if you found it, and I'm sure this is not the optimal one, so I'm sure that if someone who's better at sort of these types of optimization problems were to try this, you could come up with better sets T. So this is sort of this ad hoc piece I was referring to, this ad hoc piece of the construction I was referring to earlier. And by the way, this T sort of now has area basically 7/24, but if you now came up with a better T, having sort of a similar property but larger area, you would already immediately improve the constants in those bounds. So really, this sort of line of approach is sort of the new thing, and so I don't think our construction of T was optimal here. Yeah, but I'm out of time, so thank you to all of you for coming.